Hi there guys, and welcome to this video on natural logs and a little number called Euler's number e. So to understand this whole process we really need to get a good understanding of what we mean by the inverse. So if we take squared for example, what's the inverse of squaring something? Well, that is square rooting. We don't often write the two. Cubing, we'd have cube rooting. Multiplying by 5, dividing by 5. So a fifth which is dividing by 5, as this is going to be timesing by 5, and the inverse of subtracting 8, of course, is adding 8. So let's think of the graphs. So if we were to sketch the line y equals 2x, label my axes, we can have a nice linear line. I'm going to actually do this relatively properly, something like that. Well, that is 2 times the variable, so the inverse of timesing by 2 would actually be halving. So half x would be the inverse of timesing x by 2, right? And that would look something like so. Let's have a look at x squared. So I'm going to just draw a bit of a dodgy axes again. So x and y. And x squared is a nice happy parabola. That's not bad, I'm pretty happy with that. And square root, well, that's a bit trickier. So if we think about it, if we take, say, 9, the square root of 9 would be 3. So if we took, say, 4, that would be maybe a 2. So maybe like over here, 0, 0, obviously that would be the same. And what we'd actually have is a curve looking like this. Now, what we actually do with graphs, we can't have from one input 2 outputs. It's kind of like shooting an arrow at a target. You can't hit 2 different places with one arrow. We kind of have that attitude in graphing as well. So yes, numerically square root of 9 would be plus and minus 3, but in the graph we say it's only 3. Okay, I know that's a bit weird. But so if I put that line in dotted, you can see a little bit more. What's going on? So maybe between these two, and you may have some prior understanding of inverse graphs, but I'll just tell you quickly now that when you find an inverse graph, you actually get, I didn't want that colour, I wanted a different one. Let's try again. Oh, that was a very successful try. That is the line here, y equals x. So an inverse graph is always a reflection in the line y equals x. Let's check it out here. If I drew, we have to take my word for it really because there's no scale, but it looks something along those lines and it would reflect in the line y equals x. So let's have a look at this PowerPoint I've made here on letter E. The number e rather. So here's a picture of him, Leonard Euler. You can see the year which he made this. So we're learning something that people discovered hundreds of years ago. Now this is it. Okay, it's built into your calculator. This is a fraction of it. You can see there's a recurring, well, kind of a recurring pattern there, 1828, 1828, and then you've got the numbers inside an isosceles triangle randomly, and then it just goes on. It's like pi. It's irrational. But just like pi, we found a use for it. It exists in nature, and Leonard Euler did exactly the same thing, and that's why it bears his name. So, like pi, it goes on forever, but we've now calculated it to over 1 trillion decimal places. Why we would need that, I don't know. We can just gloss over this bit, but basically the message I'm trying to give you here, it occurs naturally, and that's why there was a need for this number. So let's think about what this graph looks like. So, the graph y equals e to the x, you may not know what that is, but I guarantee you know that anything to the power of 0 is 1. So whatever, so 2 to the x, this would be 1 here, and then 2 to the power 1 would be 2, 2 squared, 4, 2 cubed, 8, and it would have this pattern. Now if you think about what happens when you get to minus values, well 2 to the minus 1 is a half, 2 to the minus 2 is a quarter, 2 to the minus 100 would be really small, but it would never go to 0. So what I'm trying to do here in this area is show you where it's tending towards this x-axis. Well, e is 2.7, so that's why I started with 2 to the x. So if we go to 3 to the x, you can see there's a very similar shape, it just curves upwards a lot steeper than 2 to the x. Well, what's e to the x going to look like? Something in between, right? Because 2.71828 is in between both of those other graphs. 2 and 3 is the base value. So that's what it looks like. And remember, all of these graphs cross at 0, 1. Okay, very important observation to understand. But then you should see on your calculator, there's a ln button, which stands for natural log, log natural, maybe. And that is invented, that's probably not the right word, discovered, no, it is invented by John Napier. Okay? And what he said is if you take the log of a value, but to the base e, we have to use natural logs. So we can use logs, normal logs, when we've got a rational base value, but as soon as we use a base value of e, we have to use natural logs. Your calculator, I don't think, will work if you try to use the normal log button with e, so that's why we have another button. Okay, so we only use the natural log button when the base value is e. So let's have a look at the graph of natural log of x. Well, the log graphs, their logs are inverse to, say, powers. So we've just looked at like 2 to the x and 3 to the x. Now a log graph would be the inverse of that. So let's think about what I just told you about inverse graphs and what they're actually going to look like. And there you have it there. So e to the x is this green line here. And if we reflect that in the line y equals x, we get a log graph. And this is a natural log graph, but all log graphs will look the same. And you can see this point here, 0, 1, reflected in this line. So 1 down, 1 across. Very, very important to take note. Okay? And we've just spoke about what these two graphs look like. All of them are a reflection in the line y equals x. Okay. So before, ignore this thing about C2 here, that's old parts, that's what used to be called the A level. So before we would take logs to both sides, but now if we do that, that would be base 10. Or any base I wanted really. I could use base 2, base 3. As long as I did the same to both sides, we're not breaking any math laws. But what we could do is we could actually use the natural log. So we could, I don't think I've written it down there, no I haven't. So it could have written the natural log of 2 to the x is equal to the natural log of 9. But that would be to base e. So as long as we do the same to both sides, we will find the value of x to be the same. And then I don't know why I've put Mr. Bean there going bazinga, because it's pretty cool. Right, let's go back here then. Let's have a look at some questions now. So if we were asked to solve this, so anything with a power, we're thinking logs, right? But we have a base value of e. So you see that base value, you're going to have to write a natural log. Now, what actually happens here, well, we've got the power law, so we can bring this x down in front. So we end up with this. But the base value here, which I didn't write deliberately, is here and here. Now what is the log of anything to the same base value? It's 1. So what actually happens is this will go and we end up with x to be 5, because that'd be 1x is 5. Okay? Let's have a look at another one. So remember here, there is a base of e. When you see the natural log, the base is e. Let's go back to this fact that I always tell you to go back to. So if we wanted to write this with logs, we could say a log of 8 to the base 2, the bases always stay the same, is 3. Well, that's the same for natural logs. It's just a different name because it's a different type of base. So what we can say here is base always stays the same. So 3 is now going to be the power value, and what we're finding the log of is going to be on the other side. So x is actually equal to e to the power of 3. Okay, so we've just gone the other way there. Let's try and solve this one. So we've got an equation that's not obvious with powers, so it's logs. We've got a base of e, so it's natural log. Natural logs to both sides. Use the power law, so we can bring down 2x plus 3, and we end up with natural log of e. Remember, that is to a base e, so that's going to go. So to find out what x is, so is going to be the natural log of 7, take away 3, that would give me 2x, so I divide by 2, and I have a nice exact answer for x. Okay, let's have a look at another one. So we really can't begin to find x in this form, I'll just put the e there, until that's the subject of the formula. Okay, so let's make that the subject. So if we take away 1, we'd have 4, we'd half it, we'd get 2. So again, using our knowledge of here, and I'm just going to write natural log here. Actually, no, that won't make any sense because I'll be writing natural log with a rational base. That's just bad practice. So that would be the same. Okay, so always come back to this when you get stuck. So the base value is still the base value. We're going to raise it to 2, and that will give us x. Nice exact answer. I wouldn't bung it in my calculator because that's better than rounding. Okay, here's a fun one. So, little quadratic in disguise, like the last lesson. So let y equals e to the x. Well, what we actually have here, well, that's definitely 5y. And I'm going to bung the 14 over because on quadratics or anything non-linear, we make it equal to 0. But I need you to recognize that e to the x squared, because of the power law, that is the same as e to the 2x. So that must be y squared. Well, let's factorize now. So y plus 7, y minus 2. So we get two values, minus 7 and 2. So therefore e to the x is minus 7 and e to the x is 2. Right. So you should know that anything raised to any power can never be negative. It tends towards the x-axis. But this one can work. So now we've got to solve this. So we take natural logs to both sides. Bring the x down. This is equal to 1 because you've got the same base value there. So you don't have to put the base value in when you use your calculator. You can just put natural log of 2. Okay, natural log automatically uses base e. But there's the answer. So x is the natural log of 2. That's a nice exact answer. So I think that's the last one I'm going to show you. Yeah, you just need to go and practice. I'm going to pop some questions on for you and enjoy.